Why? Because that group changes its spectrum. So we actually can follow the electron passing this 2 iron, 2 sulfur center and going on to a heme. The in-between part, again, is just like in mitochondria, R groups and peptide bonds that this wave, this electron is going through. Cool? So in comes a PQH2. 1 electron goes up because plastocyanin, which has the copper, can only carry 1 electron. As 1 electron goes up, 2 protons get released at this enzyme active site because wherever there's a transfer, it's being catalyzed by this portion of the complex, which is the same as saying you're an enzyme active site. So it's dumping 2 protons off onto the lumen, to the interior. The pH difference between the lumen and the stroma is going to be about 3 pH units, which is a 1,000-fold difference in protons. So this thing is really creating a lot of protons. Not 3 or 4, 1,000 times more protons in the lumen. And down here, just like in mitochondria, this plastoquinone can pick up a proton as part of the cycle. Let's just refer to your Q cycle that we had before in mitochondria. So that brings us to this, which is basically the same thing as we saw in mitochondria. They're just showing 1 cavern. And one of these strange hammer proteins, and plastocyanin for a moment has bound and it picks up the electron, and it leaves. Plastocyanin is not part of the complex. It just binds to the complex. So the Q cycle is weird, but it's important to talk about it because it's important in 2 biological processes. Can't get around it. Okay, here's photosystem 1. This is the guy that's going to make, down here, ferredoxin. Ferredoxin is not part of photosystem 1, nor is plastocyanin. Plastocyanin has just come over, carrying 1 electron, and now when it comes to this part here, the electron can go down either side. So photosystem 1 is symmetrical. I should have mentioned this on our previous slide of photosystem 2. You know photosystem 2 has that OEC complex. The electrons are only running down 1 part of that diamond. We don't know why that is. Here, the electron that comes down can run down either side of the diamond in photosystem 1. It's kind of weird in photosystem 2. You bring 2 things together. You might think the organism would use both sides. But in photosystem 2, one of our first slides, the electrons are only coming down 1 side. Here, 2 giant subunits. Again, they call it subunit A, but subunit A has many subunits that are making it up. Subunit A and B are identical, and the electrons can flow down either path. So here comes plastocyanin bringing 1 electron. It's going to give that electron to the chlorophyll dimer. This chlorophyll dimer needs a photon of light, shown here as an exciton. This pumps it up to enough energy to pass it in the Z-scheme to this chlorophyll, which then goes to the quinones that we talked about, to this iron-sulfur complex. So when an electron comes in here, this dimer says, thank you, just replace the electron that I kicked off previously. So what we're seeing here is what the Z-scheme mechanically is doing. Okay, so now this electron comes down to ferredoxin. Ferredoxin can carry how many electrons? Just 1. So 1 electron is coming down through here, loading up ferredoxin, which then, this is going to take it to that enzyme, which is going to take 2 of these ferredoxins to generate 1 NADPH. Who cares about NADPH? The plant needs almost as much NADPH as it does ATP to make a sugar. So the ATP synthase can be making all sorts of ATP, but without this making NADPH, the plant can't make glyceraldehyde 3-phosphate. So that brings us here to our last slide, which summarizes a lot of what's going on. Let's just calmly look at this. If Lehninger wants to show one NADPH being made, and again, it's a continuous stream, but if you want to show as humans one NADPH, how many electrons do you need? 2. So, how many plastocyanins do you need? 2, because they can only carry 1 electron at a time. Now, why am I doing this? I'm trying to get back to here, where you're creating 4 protons at cytochrome B6F. Because just like in the mitochondria, when one PQH2 binds, 1 electron goes up onto plastocyanin. And when it does, it dumps off 2 protons. But you're going to need 2 plastoquinones, PQH2s, because you need 2 electrons, 1 at a time, to plastocyanin. Are you with me on that? That's the tricky part. So if we go backwards, we go, oh, so I need 2 of these plastoquinones. That explains why Lehninger has 4 protons coming off here instead of 2. Because PQH2 has to bind twice. Each time it binds, it dumps off 2 protons. Here, at the oxygen evolving complex, this thing, you can think of this as H2 being H dot twice. This thing was only donating 2 protons. So between the two donors of protons, cytochrome B6F is donating twice as many protons. He's the guy who's really contributing the most to the proton gradient between the 2. Cool? And now this runs, I wish they wouldn't just run it right through like this. Remember, this goes through a half channel and then out on the other half channel. This half channel thing is the same. And CFO and CF1, O instead of 0 for oligomycin. This is the chloroplast FO, and this is the chloroplast F1. They're very similar, but because they're in chloroplast, they have slightly different amino acid sequences. And so we're left with this situation down here. I would like you to know this stoichiometry, because this tells us that we truly understand what all of the preceding slides are saying. So we see, and that's why I put out here on the right in red, this system is creating ATP in a 3-to-2 ratio that we said is necessary for the enzymes that are in the stroma that are going to take this particular ratio of ATP to NADPH to build a sugar. So next time, we'll talk about how the plants out here in the stroma, the negative side out here, how the enzymes make use of this 3-to-2 ratio. Okay? So I'll see you next time.